Hey guys, so in this video we are going over lesson 1.2. In this lesson we're going over transformations of quadratics. So remember, the expectation from this video is to write everything down and come to the live sessions with questions. I may not do all of the notes on this document that you have access to from the newsletter in the weeks to do, but the rest of it will be taken care of it during the live sessions. So the first thing we want to do is go over some key terms, kind of a review from 1.1. So the parent function. The original function before it is transformed. The parent function is y equals x squared. So when we transform a quadratic, we are going to start with our parent function, which if we put into a calculator, and how we put this into a calculator is going to Google. And if we go to Google, we can hit Desmos, so Desmos. Hit the first link that pops up and hit graphing calculator. Now you can use a physical graphing calculator to do the same thing. You can use some of the online calculators as well. But so you can see it easily through my iPad, I'm going to use Desmos for the video. So we're going to type in our parent function, y equals x squared. And then I'm going to use my finger, or you can use your mouse, to scroll through all of the ordered pairs or the points on the graph. So that is how you can find these points that we are going over. So if you go to x is negative 2, you should have y is 4, where x is negative 1, y is 1. When x is 0, y is 0. When x is 1, y is 1. And when x is 2, y is 4. So we're going to graph this. Negative 2, 4. Negative 1, 1. 0, 0. 1, 1, and positive 2, 4. So our parent function is looking like this. Now, what if our a, and when I say a, I'm talking about our standard form, y equals ax squared plus bx plus c, where our a is now negative, versus our number 1, or our parent function, was positive. What is it going to look like? How is it going to change our parent function? Well, if we go back to Desmos, and instead of positive x, we threw in a negative, it flipped on us. But if you look closely at some of the points, all it did was flip it, made the y's negative. The x's stayed the same. So when we have x is negative 2, y is now negative 4. When x is negative 1, it is now negative 1. When x is 0, y is 0, because you can't make 0 negative, it's just itself. When x is 1, y is now negative 1, and when x is 2, y is negative 4. So we're going to graph this as well. Negative 1, 0, 1, 1, negative 1, and 2, negative 4. So there is your graph. And again, it transformed from our parent function, which was number 1, to number 2, because there was a negative in front of our a, or our a was negative. So in Desmos, graph the equation y equals 4x squared. How does this compare to the graph of y equals x squared? So before I go to Desmos and graph that 4x squared, I want to graph my parent function. So I'm going to use those ordered pairs. And in red, I've got 0, 0, 1, 1, and 2, 4. Got 1, 1, 2, 4 here. So there is my parent function on my graph. Now I'm going to go to Desmos and type in, actually I can keep my parent function there, do y equals 4x squared. So it got really skinny compared to my parent function. So let's graph this. Let's see some whole numbers that I can graph. So if I hit the blue graph on mine, it may be a different color on yours. Still have 0, 0. And if I drag my finger or drag my mouse over the graph, I get 1, 4. And another point that I can use is that negative 1, 4. So using a different color, I'm going to go 0, 0. And then it was negative 1, 4, and 1, 4. So this is what my new graph looks like. So how did we change from the red graph to the blue graph? We vertically stretched it. So we took the top of the red one and stretched it and made it skinnier. So let's look at another one. What if our function or equation was y equals 1/2 x squared compared to our parent function? Again, I'm going to go in with red and put our parent function down. And no, it does not have to be perfect, as long as you know where those few points are. Keeping that parent function as red. Let's do 1/2 times x squared. So that blue is our new graph. Let's get a few whole numbers as our ordered pair to put down. Negative 2, 2. And then we've got, should be about positive 2, 2. And you can get it perfect. There you go. So we're going to come in here with a different color. Still got 0, 0 as our vertex. Negative 2, 2. And positive 2, 2. So if you see a little bit of it, it got a little bit wider. So how we're going to name this transformation is that it vertically compressed. So a way to remember this is if we started with the red parent function and we took our hand and we smashed it, or we compressed the two sides of the red graph a little bit down, it would create that blue graph, that 1/2 x squared. What conclusion can we make about how the value of a in our parent, or in our standard form, y equals ax squared plus bx plus c, affects the graph? So in your notes, you need to write if a is greater than 1, the graph stretches vertically. If a is less than 1, the graph will compress vertically. So there is your conclusion of whether a is less than or greater than 1. So let's look at some examples of this. So if we look at this, order the functions from narrowest graph to widest. Use Desmos to graph. So we're going to be looking at the absolute values of our a's. So we're working with, let me erase that. We're looking at absolute value of -2. We're looking at absolute value of 1/3, absolute value of 6, and absolute value of 0.2. So that means we're looking at +2, +1/3, +6, and +0.2. So the greater it is away from 1, the narrowest it's going to be. So we want the biggest number to be our number 1. Well, which number is bigger? 6. So that's going to be our narrowest. So 1, and that's going to be narrowest. Now what's the next biggest number? We can mark this out now that we've already used it. So number 2. So whichever one had 2 as the a, which is this one up here, this is going to be the, so first narrowest, second narrowest, so on and so forth. So the next biggest one we have is, we've got in between 1/3 versus 0.2. So let's talk about this. 0.2. How else can we write 0.2? Write 2 over 10 because it's in the tenths place. Simplify this to 1/5. In between 1/5 and 1/3, which one is biggest? Which one is bigger than the other one? Well, 1/3 is bigger. So this is going to be the third. And number 4 is going to be the 4. So this one is actually going to be the widest of all of these. Moving on. So in Desmos, graph the equation y equals x squared plus 4, and we're going to compare it to our parent function. So let's draw our parent function. Let's go to Desmos and type in our new equation. And we have x squared plus 4. So if we zoom out a little bit, we can see our graph. And again, how to find the specific points in Desmos. You can drag your finger all up and down the line to find the perfect ordered pair with whole numbers. But it should look like something like this. where your vertex or your min is there. -1, 5, and 1, 5. And -2, 8, and +2, 8. And that should be your graph. So we need to figure out, how did we change in between the red and the blue? Well, if you look and identify our vertex in the red graph versus the blue graph, how did it change? Did it move down? Did it move up? Did it move left? Did it move right? It moved up. Did all other points move up? Yes. So your point 1, 1, or -1, 1 moved up 4 spots. 1, 2, 3, 4. So all points moved up 4. So we're going to call this transformation shifted up 4. And that's how you would write it. So let's do another one. What if it was instead x squared minus 3? So let's look at this. Let's go to Desmos. So instead of going up 4, we went down. And we went, did I type it in wrong? Yes, I did. Should be 3. So we went down 3. So parent function is here. And then our new graph was here. There you go, and you can obviously use your ordered pairs to do this from the graph. Now, how did we shift from the red to the blue? Hopefully you can tell. We shifted down 3. Now, what can we conclude looking at the equation we used to transform this one? And also, if I can get it to go to the other page, what we used to transform the last one to go up 4. Hopefully you figured it out. If it was positive, we went up. If it was negative, we went down. And that's kind of what we have right there. If k was positive versus if k was negative. So let's look at some examples. If we had x squared plus 3, well, we have a plus 3, not with the x, so we're going to be shifting up 3. The domain is going to be negative infinity to positive infinity. And the range is going to move because typically our parent function is going to look like this, where our range is 0 to infinity. Well, if we're shifting up 3, that means our smallest y value is going to be at 3. So our range is going to be 3 to positive infinity. And that is how you do that. For number 2, we've got a negative instead of a positive. So we're going to be shifting down 2. Domain is always negative infinity to positive infinity. That is not going to change until we get into word problems. And then your range, again, is going to go from here, and it's going to go down. Your smallest y value is going to be at negative 2. And that is how you do number 2. Going on. So in this case, we are looking at y equals parentheses x plus 6 squared. So parent function. And then the new graph is going to be here. You can use Desmos to graph this. But there is your new graph if you checked Desmos. So how did we change in between the red and the blue? We shifted left 5. Oh, 6, my bad. Now, I'm going to give you a little hint after we go over the next one. So, hold tight. In this one, if we graph our parent function, which is that y equals x squared, it says it in the directions of this one. Our new one is going to look like this if we graph it into Desmos or a graphing calculator. Yeah, okay. So how did we move? How did we get from a red graph to blue graph? All points shifted to the right 4. Like our vertex shifted over 4. Our negative 1, 1 shifted over to 1, or shifted over to 3, 1. Our negative 2, 4 shifted over to 2, 4. Then our 2, 4 shifted over here to 6, 4. So with these, the conclusion is that if our h is positive, then we're moving to the left. If it is negative, we're moving to the right. So a trick is that if you think of a x-axis, x-axis is here. On the left side, are x's positive or negative? Negative. The right side of an x-axis, are x values positive or negative? Positive. So if you are given an equation, x minus 2 squared, this negative 2 is on the inside, it's with the x's. If it is negative, you're going to go the opposite way of the negative x values on the graph. So a negative with the x, you're moving away from the other negatives. So this is going to be moving to the right. Now what if you're given y equals x plus 2 squared? Well, because on the inside with the x, you have a positive, you're going to be moving away from the positives on the x-axis. So you're actually going to be moving left if it's positive and in the parentheses. So let's go over some examples. And it's all the way up here. So for number 1, we have a negative on the inside. So on the graph, on the x-axis, here are the negative x values, here are the positive x values. We're going to be moving away from the other negatives. So we're actually going to be moving right 7. So that means our domain is negative infinity to positive infinity, again, always. And then our parent function, our range, was 0 to positive infinity. Well, if we move right, and it looks something like this, does our lowest y value change? No. So it's still 0 to positive infinity. Moving on to number 2. So we have a positive number on the inside with the x's. So if we have our x-axis, all positive x values are on the left side. All negative x values are on the left side. All of the positive x values are on the right side. We've got a positive on the inside with the x. So we're going to be moving away from all the positives. So we're going to be moving left 2. Our domain, always. In our range, same situation with the first one. If we move left and right, it's not going to change our y values. So we're going 0 to positive infinity. All right. So in this case, we've got 2 things going on. We've got to deal with this 2 on the outside. This is acting as our a. So our x is representing this whole parentheses, but our 2 is still our a. So that 2, absolute value of 2, is greater than 1. So what transformation are we going to do? A vertical stretch. Now what about this negative 4 on the inside? We're going to go away from the negative x values on the x-axis. So we're going to be moving to the right 4. So what is our domain? Domain always, because we weren't given any restrictions. And our range. So that stretch or compress is not going to change our range. It just depends on it being skinnier or wider. Our range does not get affected. But if we do move left to right, does that affect our range? Well, if we move to the right from our parent function, do we have a smaller or bigger y value as our lowest? No. Our lowest point on our parent function was 0. Lowest point on our transformation is also 0. So our range stayed the same. Now what about number 2? Number 2, we got a lot of things going on. Let's color code as much as we can. 1/2. Well, absolute value of 1/2 is less than 1. So that means we're going to have a vertical compress. What about this +3? Well, on the x-axis, we're going to go away from the positive x values. So we're going to go to the left. And then with this -8, we're on the outside. So we're going to be going down 8. So with our domain, we've got the same thing as we're used to. And the range, well, we kind of talked about it in number 1. The stretch and compress is not going to change it. The left versus right is not going to change it because it's not going to change our smallest y value. But if we move it up and down, it will. So if we go from our parent function to our transformation, that lowest point is now going to be 8. So now we're going to go from -8 to positive infinity for our y values. And that is your 1.2